Okay, so in this lecture, I'm gonna give you a quick tour of a state. Namely, I want to talk about this question: what is a state? And a typical way of writing down a state in quantum mechanics is use this thing called the. Actually, this is not a bra. Anyway, I'm not sure what's the best way of calling this. But this is the usual way of expressing a quantum state in quantum mechanics, and and the notion of a state is sort of the foundation of quantum mechanics. So, by foundation, what I mean is that quantum mechanics is defined in terms of these object called a state. It's not that the state is defined in terms of quantum mechanics. So hopefully, maybe this analogy will help you. In Newtonian classical mechanics, so this is sometimes called the Newtonian mechanics, or also sometimes called the classical mechanics. The foundation of the classical mechanics is this thing called the coordinates. And Newton's law, which I'm sure you know very well, is about how how this object called the coordinates of a particle evolves over time. And the rule that governs the evolution of these coordinates is is nothing other than the second law of Newtonian mechanics, also called the force law, which tells us under a given influence of a force how the coordinates will evolve over time. So as a function of time, t, the Newton's second law, if we know how to solve the Newton's second law, then we will also know how these coordinates of a particle will change over time. So that's a very, very practical and pragmatic way of saying what Newtonian mechanics is all about. And so when you think about Newtonian mechanics, the notion of a coordinate is something you sort of have to take for granted. Okay, so the coordinates is the mathematical or the conceptual thing with which you describe the particles. So, sort of in the same vein, the quantum state, which I wrote using this funny notation, is the object or the concept with which we choose to describe the dynamics of a quantum mechanical particle or quantum mechanical phenomena in general. Okay, so similar to Newton's law, there is some equation which governs the time evolution of these quantum states. And I'm sure you have heard of this. This is called Schrodinger's equation. It looks like that. And if you don't already know what quantum mechanics is, this equation will probably mean nothing to you. And I hope to be able to clarify over time what these funny symbols really mean and how you can actually even solve such an equation. But for now, we can say that as long as we know how to solve this, then what we know or what we learn from solving these Schrodinger problem is the way in which this quantum state will evolve over time or as a function of time. Okay. Okay, so in some sense, there's a pretty close parallel between the way that the Newtonian mechanics treats the evolution of coordinates and quantum mechanics treats the evolution of quantum states. So in some sense, this is like the coordinates. Okay. So maybe I can elaborate a little bit more. In classical mechanics, basically every particle is regarded as a point. And as long as it can be regarded as a point, then its physical properties are sufficiently well described by giving out the coordinates of a point particle at any given time. Okay, so we can set up this coordinate system, x, y, and z. And somewhere in this coordinate system lies this particle. And although I have drawn it as a circle, you should really think of it as a point that has no extension whatsoever. And over this space of Cartesian coordinates, this particle evolves along a certain trajectory like this. Okay, and just precisely what trajectory the particle's coordinate follows is, of course, entirely governed by the Newton's law and what kind of force acts on that particle during its motion. In quantum mechanics, particle is still point. So the point particle view is still upheld in quantum mechanical picture, but the key difference is that the location of a particle is never exactly specified. Never. It's never exactly known. Okay, so perhaps you may have heard of the Heisenberg uncertainty. That, or you may have seen some formula that states some sort of inequality like this. Well, okay, whatever. I mean, the Heisenberg uncertainty relation is not really anything that's independent of quantum mechanics itself. Heisenberg uncertainty is just a consequence or one of the many, many, many consequences of the underlying laws of quantum mechanics. So you can say that the uncertainty relation is just a consequence of the Schrodinger equation. But because this terminology is so popular, Heisenberg uncertainty and so on, that people tend to think that the uncertainty relation is some sort of the foundation of quantum mechanics. I find that statement actually quite misleading, and for that reason, I will try not to talk about the uncertainty relation or even use the term uncertainty. Uh, so the reason I'm talking about it now is because I assume that many of you have come to this class kind of knowing or having heard about the Heisenberg uncertainty relation, but without really knowing uh, without knowing too much about the Schrödinger equation or the notion of the state itself. Okay, so what I'm hoping that you will acquire from this lecture is the proper notion of a quantum state and its temporal evolution according to the Schrödinger equation, and as you do that, you can also kind of start forgetting about this Heisenberg uncertainty as some sort of fundamental principle of quantum mechanics. Okay. Anyway, so it's so the funny thing about quantum mechanics is that although it still presumes that every quantum particle is described as a point, but at the same time, it abandons this Newtonian way of describing the particle's dynamics in terms of its coordinates, because, as I said, the coordinates of a quantum mechanical particle can never be precisely identified. So instead, people come up with a quite different interpretation of quantum mechanics, uh, namely that instead of the coordinates itself, there's something called the probability amplitude. Have you heard of that? Amplitude. And amplitude is some sort of complex number. So this is a complex number consisting of the real parts and the imaginary part. And this wave function is somehow supposed to represent the probability with which to find a particle at a certain location. Okay, so probably the version of quantum mechanics that you may have heard is that there is this a complex valued function which depends on the coordinates and time, and whether a particle should exist at that point, at that time, is given by the square amplitude of these complex valued wave function. Okay, so this is a probability to uh, this is the probability to find a particle at the location R at the time t for that quantum mechanical particle. Okay, but since this is a probability, a particle can be found in lots of different places, just with different probabilities. So in that sense, even a point particle can be spread out over a rather wide region in space. Okay, so a point particle can be spread out. And this is probably one of the ways in which you can get confused by just exactly what the quantum mechanics is doing in describing the motion of particles. Because on one hand, we say that it's still a point particle down in the quantum world, but in a different scheme, we say that a particle can be spread out over many different places at the same time. Okay, I mean, this is pretty confusing, right? Our traditional view of natural world is that either something is here or it's there, right? It's not like a particle may be here, but it can also be here or here or here. This is not the way we view the world. But what quantum mechanics is telling us is that this kind of view is simply wrong. And this is just not the way to understand how the atoms work or how the molecules work. So it no longer matters whether you find this picture understandable or acceptable, because if you choose not to accept it, then you become a loser. So I'm sorry to say that this is a kind of this is something like a religion, right? You may not like the way that the rules of a religion is laid out, but this is just this is the way things work. So I should not be confusing you in saying this, because I'm not saying that quantum mechanics is like a religion in the literal sense. The rules that we have discovered for quantum mechanics really works very well in describing how the quantum world and the world of atoms work. Okay, so everything that we say in quantum mechanics has been tested by 100 years of careful experiments. So in that sense, it's nothing like religion. But this, when I say it's kind of like religion, what I really mean is that although the way that this quantum mechanics is being explained to us is not intuitive, like a particle being both like a point, but at the same time being spread out over space, is not intuitive at all. It doesn't really agree with our everyday experience, but you have to accept that as the more fundamental truth. So in that sense, it's a bit like religion, in the sense that you have to believe in things and principles that you don't get to see with your own eyes, or get to listen to with your own ears. Because what you learn from your own experience is quite limited. Okay, so that's why I keep saying that this notion of a quantum state is something you just have to take for granted, something you have to believe in. And then once you accept that such a thing does exist, then what you have to do from that point on is to work out the consequences, uh, and try to understand everything that goes on in the quantum world in terms of these object called the quantum state. Okay, so in this video, I try to give a somewhat philosophical introduction to what quantum mechanics is all about. And I'm sure I have confused you more than I have enlightened you, but that kind of confusion is partly intentional and also unavoidable, because I'm being quite honest with you that quantum mechanics does not have a foundation that is intuitively obvious. So there's a point at which you have to take certain things as granted, even though you may not like the way it's phrased. Okay, and so hopefully, as my lecture evolves, I will get down to more solid formulations of quantum mechanics, and you will get to appreciate how, starting from this weird object called the quantum state, I can kind of explain a lot of things that goes on in the quantum world.